Let's revisit the tank filling problem, but with an arbitrary source term, in addition to the flow out the sink term. So the setup is the following. We have a tank with a drain, and the flow out here, flow out, is proportional to the height of the water in the tank. Where lambda is the proportionally constant, is greater than 0, and the dimensions of lambda are an area per unit time. To this we add a flow in, and this time it will be a function of time. So some function of time that remains to be specified. So to set up the differential equation, it's a matter of writing down the expression for the conservation of volume. So that means that the time rate of change of the volume is equal to the flow in minus the flow out. And the volume of the tank, V, is equal to A times H, and A doesn't depend on H or time, so A is a constant. So this gives us A and to this we must add an initial condition, and we'll say that at time t naught, the height of the water in the tank is some constant h naught. So this is the problem we want to solve. And this time the difficulty is that, well, we can't just integrate both sides because h is an unknown function, and we can't separate variables because the right hand side here depends on both time and h. So the method of separation of variables won't work either. One thing we can do is to check see if the equation is an exact equation. So let's do that. So we check to see if, and let's give this a name, 1. So we want to see if that equation is exact. And so in terms of the differentials, we have A dH minus R of t minus lambda h dt equals 0. And if it's exact, then there has to be a function whose partial derivative with respect to h is equal to the coefficient of the h, and whose partial derivative with respect to t is the coefficient of dt. Remember, for a differential, deep psi is deep psi dh plus deep psi dt. So if there is such a function of h and t that can be written out as this form, psi is a constant, then I need deep psi dh has to be equal to a, the coefficient of dh, and deep psi dt has to be equal to the coefficient of dt. And if there is such a function, then if I take the derivative of this one with respect to t, the partial with respect to t, and if I take the partial derivative of this one with respect to h, they should be equal to each other because they'll be the same mixed second partial derivative. So let's compute those derivatives and check what we get. So this means that the second derivative dt dh, so the partial derivative of this respect to t is just 0 because a is a constant. And on this side, if I take the partial with respect to h, what do I get? I just get lambda. And these two need to be equal if the equation is going to be exact, and so lambda is some arbitrary constant, is some function constant, and in general it will not be 0, and so the equation is not exact. So lambda is not 0 in general, so the equation is not exact. So what we do in this case is we introduce what's called an integrating factor. So we're going to multiply this equation through by some function of time, and we're going to see if we can force the equation to become exact. So we introduce mu of t, so mu, the Greek m for multiply, an integrating factor. And we multiply through the equation, and we're going to see what conditions we can derive on mu to make the equation to be exact. And what we get is mu of t a dh minus r of t minus lambda h mu of t dt has to be 0. And so now if I'm going to check the mixed partial for my function psi, I have d psi dh is equal to a times mu, and d psi dt is equal to minus r of t and I'm going to take the mixed partials. So what I get is d2 psi dt dh is equal to a times d mu dt. Remember, mu is a function of time. And from this one, I get d2 psi dh dt is equal to lambda mu, right? Minus makes it a plus. Lambda h mu, partial with respect to h, we'll get rid of the h, and I'll just get plus lambda mu. And now if the equation is going to be exact, this has to be equal to that. So for exactness, I need and so I had a differential equation. I couldn't solve it. I introduced the integrating factor, mu, multiplied through, and I derived a condition on mu to make the equation exact, and that is itself a differential equation. Now the nice thing is that this differential equation is easy to solve. This one, maybe you can just see the solution. It's going to be the form of an exponential with respect to time, right? The derivative of a function is just proportional to the same function. That's true of the exponential function. But we can also separate the variables to see that it is indeed an exponential, that is a solution. So before I proceed, I'm going to introduce this variable tau, which is going to be a over lambda. Remember, a is an area, and lambda has dimensions of area per time, so a over lambda is going to have dimensions of time. And so I'm introducing this parameter tau here, just to simplify the notation. And then the equation will become d mu dt is equal to mu over tau. And if we separate the variables, I'll get d mu over mu is equal to dt over tau. Tau is a constant. If I integrate both sides, I get the natural logarithm of mu is equal to t over tau. And then if I exponentiate both sides, I'll find that mu of t is equal to e to the t divided by tau. So this is my integrating factor. And if I multiply the equation through by this factor, the equation should become exact. So let's try it. So then I have my equation, and I'm going to keep the variable tau in the equation. So I have dh dt is equal to r over a of t minus h over tau. So that's the equation. I've just rewritten it using the constant I defined, tau. Now I'll multiply through both sides by the integrating factor, and what I get is and I will integrate by parts on this side. And I do that by bringing the e to the t over tau inside the derivative, and then I have to subtract off the derivative with respect to this expression multiplied by h, using because of the product rule. So then this becomes d by dt e to the t over tau times h. And so if I use the product rule on this, I'll get this times the derivative of this one, which is what I have, plus the derivative of this times h. And so I have to subtract that term off because it doesn't appear up here. So minus 1 over tau e to the t over tau times h equals the right hand side, e to the t over tau. Oh, I multiplied the e over tau twice here. I made a mistake, right? This should not be here because I have it on the outside of the parenthesis. Times r of t, all divided by a, minus e to the t over tau h over tau. And this term and this term, they cancel. So that's true precisely because I chose my mu to be e to the t over tau. I picked it so that this cancellation would happen. And then what I'm left with is, on this side, I have an exact differential, e to the t over tau times h, and on this side I have something that doesn't depend on h. So now I can integrate both sides. This one respect to t, and this side also respect to t, and I'll just get what's on the inside. So if I integrate at this point, what I get, so my equation now is d by dt and I integrate both sides from t naught out to t, dt primed, and same thing on this side, from t naught out to t with respect to t primed. So the integral on this side is easy. That's an exact differential, so what I get is e to the t over t primed over tau h of t primed evaluated at t naught and t, and same thing on this side. Well, this one I don't, until I specify r, I can't do the integral, but in general, if I was given a specific function for the flow into the tank, then this integral could be evaluated because it depends only on time. So I'll just leave it as an integral. T naught to t e to the t primed over tau r of t primed, dt primed. And now I'm just going to evaluate this at the two limits. So what I get is e to the t over tau h of t minus e to the t naught over tau h of t naught is equal to, and then rearranging some more, I get h of t, and I'll divide through by e to the t over tau. So we'll divide every term, so it'll be gone here. This one, which I'm going to now bring to the right hand side, is going to be a plus e to the minus t naught divided by tau h of t naught. So that's this part here. After dividing through by e the t over tau, that makes it e the minus t over tau plus the integral from t naught to t. And if I divide through, I can bring the factor of e the minus t over tau inside the integral, because this is an integral with respect to t primed, and this is a function of t. So this becomes e to the minus t primed over tau r of t primed. And this is the final solution. And so the form of the solution is interesting. If there was no source in the tank, so let me bring back the picture here. So if I had no inflow, if r was 0, then the solution would just be this form, and it's in the form of just an exponentially decaying solution. So at time t naught, the height is h. Oh, h, and this I know, this is h naught, right? So I could have replaced this by just h naught. And so the height at time t naught starts at h naught, and then the water level just decreases exponentially starting from the time t naught. So the bigger the time interval from t naught to t, the more the level has dropped. And then the force part of the solution over here looks like the integral is like a superposition, like a sum over a whole bunch of solutions of this form, but whose initial values are somehow r divided by a. Right, so this would be, it looks almost like this expression. If I think of RT prime over A as H naught, and then I have this decaying part. So the way to think about it is that this is adding some water, changing the height, and then you let that decay. And the next time step, or next time interval, you add some more water that changes the height, and then you let that decay. And because the original equation is linear, then the form of the solution can be viewed as a superposition of solutions to the homogeneous part. And so anyways, this is the solution for the tank problem.